this video, I am going to explain how I have used data analytics and machine learning techniques to predict traffic fatalities. Our main objective is to predict fatalities, so we are mainly concerned with two factors. Out of the total fatalities, how many of them we predicted correctly, and how many of the total predicted fatalities were actual fatalities. So this is a classification problem, and more specifically is a binary classification problem which has two outcomes. The true outcome is that it is a fatal accident, and the false outcome is that it is a non-fatal accident. The performance measures we will be using are several. The first one is the precision. So the precision is the fraction of the relevant instances among the retrieved instances, which is the true positive divided by true positives plus false positives. And the second metric is called recall or sensitivity or true positive rate. It is the fraction of the total amount of the relevant instances that were actually retrieved. And the third metric is the F1 score. It conveys the balance between precision and recall. The fourth one is AUC, which measures the area under the ROC curve, also known as receiving operating characteristics curve. So what is the ROC curve? The ROC curve plots the true positive rate, which is recall, against the false positive rate, where the false positive rate is on the y-axis and the false positive rate is on the x-axis. The AUC measures the degree of, or is a degree or measure of the probability. It tells how much the model is capable of distinguishing between classes. The higher the AUC, the better the model is at predicting zeros and ones. Now, we move on to the data extraction stage. Luckily, the data has been already provided to us. So let's go ahead and use pandas to read the data. As you can see, we have a data frame at our hand. And our first look at the data frame shows that there's about several columns, and some of the columns contain numbers, while some also contain strings. This might be a problem, because we would like to deal with homogeneous types, especially machine learning models, which only deal with numerical values. So that's why I have decided to start data cleaning before the train test split. What I did was to replace all of the string values, which signifies unknown or not provided, as null values. And after I replaced all of the string values with null values, I immediately split our data into two sets, a train set as well as a test set. The ratio of the train set and the test set is 4:1, which is in accordance with most of the machine learning conventions. And after our train test split, we can move on to the data exploration stage. So what I did was basically to plot a scatter matrix. So what is a scatter matrix? It allows us to signify the attributes that we are interested in and plots all the attributes against each other, while also plotting all the attributes distribution as a histogram in its diagonal axis. As a result, if there's any interesting pattern, we can find it immediately. While looking at the data closely, we notice that our response variable, the collision severity, has a lopsided distribution. What do we mean by lopsided? Let's zoom in on the histogram. As we see from this histogram, the fatal accident compared with the non-fatal ones is almost negligible. Well, this distribution will cause havoc in our machine learning models. What do I mean by that? Because almost all of our data sets are non-fatal, our model will not be able to properly learn the fatal cases. As a result, our model will not be able to properly predict fatal cases. What we can do is to adjust the distribution. So what can we do to adjust our distribution? Well, we could certainly remove the non-fatal cases down to a size that will result in the fatal cases being significant. But at the same time, we are removing hard collected data. So a better way is just to duplicate the fatal cases, increasing its portion in the train set while not compromising the non-fatal cases. That's what I did. So I duplicated the fatal cases about 30 times using the pandas concat function. And as a result, we can see from this distribution, again, compared with our previous one, that the fatal cases become significant. Let's plot our scatter matrix again to see if there's any patterns that we can find. Well, from our scatter matrix shows that maybe because most of our variables are categorical, there isn't any discernible patterns right now. What we can do is try to do a 4D graph. That's what I did in this stage. So I engineered a feature called vehicle age, which is the current year, 2020, minus the vehicle year, as shown here. And then I plotted a scatter matrix with the x-axis being the person's age, the y-axis being the collision vehicle, number of collision vehicles involved, and the radius of the circle being the vehicle's age. And the color of the circle shows the severity, with 1 being fatal, which is shown in blue, and the red being non-fatal, which is shown in the red, which is shown in red. So from this data, we can see that most of the fatal cases involve 10 or less vehicles, and we indeed see that there are more older car models involved in the fatal accidents, as shown in the larger radius of our circle down right for the blue bubbles. And the next stage is to pre-process our data to prepare them for machine learning. Well, I used the sklearn's pipeline function to implement this. What I did is, first of all, the data, I built 2 separate pipelines. One of the pipelines used to handle the categorical data, and the one is used to handle the numerical data. And then I use sklearn composes column transformer function to combine these 2 pipelines. To handle the null values, I use sklearn's simple imputer method, which allows me to implement different strategies for different type of attributes. For the categorical attributes, I replace the null values with the most frequent values. For the numerical attributes, I replace the null values with the mean of the values. And then I transform the dummy variables using the one-hot encoder function for the categorical variables. And then for the numerical variables, I use the standard scalar technique, which subtracts the mean value and then divides the mean by the standard deviation so that resulting distribution has a unit variance. And then our pipeline is built, and at the next stage we can start to transform our data using these pipelines. I first stacked my X train set as well as X test set from the data frame, and also I did my Y test train set, and I started my Y train set and the Y test set also, and then I put in the train set into my pipeline using the pipeline I built earlier to transform my train set and my X test set into machine learning ready data. specifically it's a sparse matrix. It's a sparse matrix that has a more efficient memory storage compared with the NumPy ND arrays. So let's start to apply machine learning techniques to predict fatality. Well, the first thing I did is to use dimensionality reduction from principal component analysis. Why did I do that? First of all, our data set, our X has about 120 features. These features will make our training extremely slow. And moreover, the more the dimensions in the training set, the greater the risk of overfitting. We don't want overfitting, so that our model will not be able to generalize. That's why we need to use dimensional reduction techniques. And I selected the principal component analysis because it allows me to preserve a certain amount of variance in my X output. So that's what I did. I tried to preserve as much as 95% of the total variance from the principal components. And I plotted the number of components against the variance. And we can see that in order to preserve about 95% of the variance, we only need 35 features. And eventually, I specified a principal components of 35, and we then transformed our X, and also transformed our X test. Then we can start to implement several machine learning models. The first one I chose is a pretty efficient one. It's the stochastic gradient descent. The general idea behind the gradient descent is to trick the parameters of the cost function until it can converge into a minimum. But one of the drawbacks of a general gradient descent is that it might only converge into a local minimum instead of a global minimum. That's why I use stochastic gradient descents, because it picks a random instance in the training set at every step and computes the gradients based only on the single instance. As a result, we are more likely to be able to jump out of the local minimum and find the global minimum. And after we fit our data, and we can start to implement certain performance measures. Because our data set is skewed, so accuracy score is generally not a good way to go for a classification problem. That's why we need to implement other metrics which I have talked about before, such as precision recall, F1, and AUC. The first thing I did is to use a confusion matrix. From the confusion matrix, we see that our precision is around 0.0237, and our recall is around 0.056. Well, our recall is okay from what we can see here. Out of the total about 900 cases, we can predict approximately 500-ish. Our precision took a huge hit. So this might not be a accurate prediction model based on the precision and recall we have so far. So let's start to talk about precision and recall. What do I mean by precision and recall trade-off? Increasing the precision reduces recall, and increasing recall reduces precision. As we see from the recall versus precision plot here, as the precision starts to increase, the recall will generally start to decrease. And as the recall starts to increase, the precision will generally start to decrease. So we can have the best of the both worlds. We can only choose one here. So we need to balance these two. And that's why we need to use other metrics as well, such as the area under the curve, in order to see how well our classifier is able to distinguish between the two classes. From the AUC ROC we have here, our AUC is generally around 0.848, which is not really a good number compared with our other classifiers. And for the following classifiers, I decided to move from a single model to an ensemble model. What is an ensemble model? It composes of a bunch of different machine learning algorithms or the same machine learning algorithms and trying to predict based on the aggregations of these machine learning algorithms. So one of the first ensemble method I use is the bagging method. What is bagging? Bagging is an approach that uses the same algorithm for every prediction. In this case, is a decision tree classifier, and then train them on different random subsets of the training sample. The sampling is performed with replacement, which we also call bootstrapping. In this case, we used 1,200 decision tree classifiers. Well, we did use a 500 and 1,000 classifiers, but the results still on the fits. So that's why I chose 1,200 classifiers. And after we fit the data, let's see the performance of the bagging. So one way to look at the performance is just to use the out-of-bag score evaluation. So because the random bagging performs a random sampling, we can just start to see the out-of-bag score will be approximately equal to the test accuracy here. But for our test accuracy is actually much higher. It's around 95.57%. But because this is mainly because our test set is different from our train set in its distribution. From our confusion matrix, we see that our precision is around 0.185, which is worse compared with our stochastic gradient descent. But our recall is approximately 0.54, which is approximately the same. So the performance of the bagging is approximately similar to what we have with the stochastic gradient descent. The area on the curve is also 0.85, which is similar to the stochastic gradient descent. The next ensemble method I used is a random forest. So what is a random forest? A random forest is also an ensemble of decision trees, generally trained via bagging. But the random forest is different with regards to bagging in the sense that the random forest has all the hyperparameters of a decision tree classifier and a bagging classifier. So we are able to adjust both the decision trees, which we use for each of the decision tree classifiers inside the random forest, and also to adjust the random forest classifier, which is an estimated number of trees grown. So we can apply regularization techniques, also called pruning, on each tree to prevent overfitting. So random forest also searches for the best features among a subset of features when stabilizing a node. So this will cause more randomization, and this allows our data to generalize better. Let's see the results of our random forest. From the confusion matrix, our precision is still pretty low. It's around 0.277. But our recall is generally the same, around 0.534. So I would say that the stochastic gradient descent, the random forest, and the bagging perform similar to each other. That's why I decided to use another different method, that is boosting. So how does boosting different from random forest and bagging? The boosting is trained with each predictors trained sequentially. So Each predictor are not trained concurrently, but rather sequentially. So only after the first one is trained will the second one be trained, and then the third, and then the fourth. And each one is trying to correct errors of its predecessors. The first boosting method I used is the ADA boost. The ADA boost tries to correct its predictor's mistake by paying more attention to the training instances that its predecessors predicted incorrectly, so the predecessors underfitted. This allows the booster to be able to correct the mistakes that its predecessors made. We used a SAM.R algorithm which uses class probabilities to make predictions. And let's see our performance measurement. The precision is actually worse compared with our random forest as well as the bagging. But our recall starts to get better. It's around 0.6. So this is the best recall we have so far. Let's see our confusion matrix. So we can see that out of the total approximately 900 cases, about 550 of them are predicted correctly. So the recall is indeed pretty impressive. What about the area under curve? The AUC compared with our random forest and the bagging is actually better. It's around 0.9. So it's better than both any of the models we have tested before. And the next one is a XG boost. So how does XG boost different from ADA boost? The gradient boost attempts to sequentially add predictors to an ensemble, each one correcting its predecessors. So in the sense, this is a boosting method. But what it uses, but how it differentiates itself is by taking the instance weight at every iteration like ADA boost. This method tries to fit the new predictor to the residual errors made by the previous predictors, rather than taking the instance weight at every iteration. And this allows the model to fit the data really well, as we can see from our performance. The accuracy score is around 97.59, but we understand that this is not the metric we use. Let's see our ROC and AUC. The AUC is significantly better. The AUC is around 0.9957, which is close to 1. This means our XG boost is able to distinguish between the cases really well. Let's see our confusion matrix. For our confusion matrix, we see that our precision is around 0.33, and our recall is around 0.587. These are all significantly better numbers compared with our previous models. The last one I used is the Ensemble voting classifier. What is the Ensemble voting classifier? So a voting classifier decides to aggregate the predictions of all of the classifiers we have so far: XG boost, ADA boost, bagging, and the random forest, and predict the result based on the highest probabilities. And then the result is averaged over all of the classifiers. In our case, we utilize soft voting, which aggregates all the probabilities predicted by each predictor and makes a prediction based on the aggregated probabilities. So it's not based on the outcome, it's based on the probabilities predicted by each one and aggregates the probabilities, most likely using mean or mode, and then predict its outcome based on the probabilities. But there are several drawbacks of a voting classifier. First of all, because we're using all of these algorithms, the training time and the complexity will be really high. That's why it will take a long time to train our voting classifier. And also, the voting classifier generally performs better if all of the algorithms that we use are different from each other. But in this case, the algorithms are pretty similar. So we are basically using boosting and a bagging with random forest and the bagging classifier. And also, because the most classifiers are trained on the same data set, they are most likely to make the same type of error. So this means that even though we are trying to aggregate their results might, because their individual results are similar to each other as a result, or the aggregated result will still be similar to each other. Let's see our outcomes. So from our confusion matrix, we see that the precision is around 0.389, which is good. And the recall is around 0.5476, which is also pretty good. Let's see our area under the curve. It's around 0.9776, just slightly behind our XG boost. So, from all of the models we have tested so far, XG boost and the voting classifier are two clear frontrunners. Let's compare these two models' metrics in order to select the best one. For the XG boost model, the precision is 0.33. The recall is 0.587. The AUC is 0.9957. And the F1 is 0.4225. Well, for the voting classifier, the precision is 0.389. The recall is 0.5476. The AUC is 0.9776. And the F1 score is 0.4549. We already knew that the F1 score prefers a more balanced precision in the recall model over a balanced precision in the recall model. But the XG boost also has a higher AUC compared with the voting classifier. So how do we choose our best model? Well, it depends on our objective here. So the objective of our case study is to be able to distinguish between the fatal and the non-fatal cases. This means that a model that is able to distinguish between these two will be able to have a better chance of being a good model. And based on the AUC, which is a metric to gauge which classifier is able to distinguish between the zeros and the ones, the XG boost model performs slightly better than the voting classifier model, even though the voting classifier model has a more balanced precision and the recall compared with the XG boost model. After we have chosen XG boost as our best model, let's try to fine-tune its threshold in order to improve its performance. First of all, let's plot a precision versus recall curve in our of our XG boost model. From the precision and the recall curve, we see that the intercepts generally around the 0.95-ish range of the precision and the recall. Well, from the metrics, we see that we would like to increase our precision a little while sacrificing little recall as possible. So that's what we did. We try to set a threshold that increases our precision by some range, but also preserve some or most of our recalls. So after choosing the threshold, we applied our threshold to the test set. And from our results, we can see that our precision has improved to 0.567. Well, we only lost about 0.08 amount of recall. and our F1 score also improved significantly. So we have significantly improved our model. In the end, our conclusion is that we are able to build a model that has a recall of 0.507 and a precision of 0.567. That is, we are able to correctly predict more than half of the total fatal cases in our test set, while simultaneously keeping the number of incorrectly predicted non-fatal cases low. This is an impressive result, considering that non-fatal cases is only 1.5% of the total instances in the test set. So here it is, and I hope you enjoy my work. Thanks. Have a good day.